take a look at an example of how we can read a phase diagram and interpret the information and apply it to solve a problem related to pressure and phase equilibrium. In this example, we're asked what is the maximum pressure in millimeters of mercury at which solid water ice and water vapor can be in equilibrium. And we're given a phase diagram for water. So before we answer the question, the strategy obviously is going to be to read the phase diagram to figure out that maximum pressure. But first, let's take a look at the phase diagram, recognize the different regions, and talk about how we can interpret the information given to figure out that maximum pressure. So in our phase diagram, remember, pressure is on the y-axis. In this case, the pressure is given in atmospheres. And oftentimes you'll see phase diagrams drawn with an uneven scale because the features of the phase boundaries don't change much over large changes in pressure. So the scales can be drawn a little unevenly, and sometimes they'll point out key pressures or important pressures or temperatures that relate to phase transitions between solid, liquid, and gas. So for water's phase diagram, we have pressure in atmosphere on the y-axis. We have temperature in degrees Celsius on the x-axis. We are interested in the maximum pressure at which ice and water vapor can be in equilibrium, which describes the set of pressure and temperature conditions under which the solid water ice and the water vapor can be in equilibrium. So our pale blue region is the solid water. Our pale yellow region is the water vapor. So we have solid and we have gas. And the idea is that as long as we have this phase boundary, which bridges the solid and the gas phase water, the two can be in equilibrium. So they can be in equilibrium under any pressure and temperature condition that lies along this phase boundary right here. But notice that as we start to go up this phase boundary, we get to the triple point of water and the liquid interrupts the two. So the way we read the phase diagram in this case is that the highest pressure at which the solid and the gas can be in equilibrium with each other is the highest pressure where the blue region of the phase diagram and the pale yellow region of the phase diagram are still touching. The solid boundary and the gas phase boundaries are touching. What's the highest pressure where that occurs? Well, after the triple point of water, the liquid phase interrupts the boundary, and then you have a solid liquid boundary and a liquid gas boundary. So the y coordinate that corresponds to the triple point of water will be the highest pressure under which your solid water ice and your gas phase water vapor can be in equilibrium with each other. And in this case, that's actually marked for us. The triple point of water occurs at a pressure of 6.0 times 10 to the negative third atmospheres. So that's the highest pressure under which solid water ice and gas phase water vapor can be in equilibrium with one another. And so we'd say this is our maximum pressure in atmospheres, 6.0 times 10 to the negative third. All we have to do to solve the problem is convert to millimeters of mercury. And our pressure in millimeters of mercury is going to be 0.0060 atmospheres. We convert that to millimeters of mercury, 760 millimeters of mercury per atmosphere. The highest pressure where water ice and gas phase water vapor can be in equilibrium with one another is 4.5 millimeters of mercury, which is extremely low pressure, not something you can achieve with typical atmospheric pressure conditions. And so we'd report that the maximum pressure where ice and water vapor can be in equilibrium with one another without liquid being present is 4.6 millimeters of mercury as an external pressure.